Bismillah ar-Rahman ar-Rahim. This video is about the randomized Kaczmarz method. We have a linear system. Ax is equal to b. A is m by n. M is greater than or equal to n. The columns of A are linearly independent. It is assumed that there exists an n-dimensional x vector such that Ax is exactly equal to b. For I between 1 and m, Ai transpose is the ith row of A. The solution proceeds iteratively. If the current iterate is xk, we choose a row I in the matrix. The next iterate xk plus 1 is the orthogonal projection of xk onto the hyperplane Ai transpose x equal to bi. The orthogonal projection matrix onto the hyperplane Ai transpose x equal to 0 is identity of size n by n minus Ai transpose. This outer product is multiplied by the scalar 1 over the L2 norm of Ai squared. If we want to project x of k onto this hyperplane, we multiply this matrix by x of k. Since bi is not necessarily equal to 0, we shift the projection in the direction of Ai using some coefficient alpha. Alpha is obtained from the equation that Ai transpose times this vector is equal to bi. Note that when Ai transpose is multiplied by this bracket, we get Ai transpose minus Ai transpose. That's a row vector of zeros. This is not surprising because this matrix projects onto a subspace that is perpendicular to Ai. When Ai is multiplied by this part, we get alpha times the L2 norm squared of Ai. Hence alpha is equal to bi divided by the L2 norm squared of Ai. Xk plus 1 is this matrix times x of k plus bi over the L2 norm squared of Ai times the vector Ai. Identity times xk is xk. We can rewrite this part as the scalar Ai transpose times xk multiplied by the vector Ai. So xk plus 1 is xk plus this scalar times Ai. The scalar is bi minus this inner product, Ai transpose xk, divided by the L2 norm squared of vector Ai. This is the update equation in the randomized Kaczmarz method. Let A dagger be the pseudo-inverse of matrix A. In our case, A dagger is A Hermitian A inverse, A Hermitian. This matrix is n by n and it's invertible, as A is assumed to have n linearly independent columns. Note that if A dagger is multiplied by A, then we get identity of size n by n. Take any n-dimensional vector z. The L2 norm squared of z is the same as the L2 norm squared of identity times z. We write identity as A dagger times A. This is an n by m matrix, and this is an n-dimensional vector. This L2 norm squared is upper bounded by the L2 norm squared of the matrix A dagger times the L2 norm squared of vector Az. Recall that if we have a matrix C, then the induced L2 norm of matrix C is the maximum over non-zero vector y of the L2 norm of Cy divided by the L2 norm of y. Since this is the maximum, then this is greater than or equal to the L2 norm of Cy over the L2 norm of y for any non-zero y. Moving this to the other side, we get that the L2 norm of Cy is less than or equal to the induced L2 norm of matrix C times the L2 norm of vector y. And this inequality is true even if y is the all zero vector. From this inequality, we have that the L2 norm squared of vector Az is greater than or equal to the L2 norm of Z divided by the L2 norm of matrix A dagger squared. Note that the L2 norm of a matrix is its maximum singular value. This comes from here. This is the maximum over vector y with L2 norm equal to 1 of the square root of the L2 norm squared of Cy, that's y transpose Cy. The maximum of this quadratic form is the maximum eigenvalue of C transpose C. The square root of that is the maximum singular value of matrix C. So the L2 norm of A dagger is the maximum singular value of A dagger. From the reduced singular value decomposition, A is equal to U S V Hermitian. U is n by n with orthonormal columns. S is n by n. S is a diagonal matrix. The elements on the mean diagonal are the positive singular values of A. V is unitary with size n by n. Then A dagger is V, the inverse of S times U Hermitian. The maximum singular value of A dagger is 1 over the minimum singular value of A. The vector Az can be written in this way: a column vector with m components. The ith component is the inner product Ai transpose Z. The L2 norm squared is summation j from 1 to m, the magnitude squared of Aj transpose Z. This is greater than or equal to the L2 norm squared of vector Z divided by the square of the L2 norm of A dagger. Multiply and divide this term by the L2 norm squared of Aj. Then multiply both sides of the inequality by 1 over the square of the Frobenius norm of matrix A. The Frobenius norm of A squared is the sum j from 1 to m, the sum k from 1 to n, ajk squared. It is also equal to the sum of the squares of the singular values of A. We can interpret the left-hand side in a probabilistic way. Note that the sum j from 1 to m of the squares of the L2 norms of the rows of A, this is exactly the square of the Frobenius norm. Those terms here can be treated as a probability mass function. We assume that in each iteration, the jth row is randomly selected with this probability. the jth row is selected with a probability that is equal to its L2 norm squared divided by the sum of the squares of the L2 norms of the rows of matrix A. The left-hand side can be written as an expectation. It is the expectation of this quantity here, the magnitude squared of AY transpose Z divided by the L2 norm squared of AY. Y is the index of the row employed in the current iteration. We assume that AX is equal to B. This means that AJ transpose X is equal to BJ, the jth component in vector B. Let's investigate the L2 norm squared of the difference between X, the true solution to this system of linear equations, and the kth iterate, xk. Add and subtract x of k minus 1. The L2 norm squared of the sum of these two vectors is the L2 norm squared of this vector plus the L2 norm squared of that vector. Then we have the cross term 2 times the inner product between these two vectors. Let's think about this inner product. We have x of k minus x of k minus 1 transpose. From the update rule, we know that this is by. Y is the index of the row used to obtain x of k. By minus ay transpose x of k minus 1 divided by the L2 norm squared of ay transpose, multiply by x of k minus 1 minus x. This inner product is ay transpose x of k minus 1 minus ay transpose x. This is by. This is the negative of that. So this inner product is minus the square of by minus ay transpose x of k minus 1 divided by the L2 norm squared of vector ay. What is the L2 norm squared of vector x of k minus x of k minus 1? This will be the square of this part. Then we multiply by the L2 norm squared of vector ay. So we get the square of this difference divided by the L2 norm squared. Comparing, this part here is exactly minus 2 times the L2 norm squared of x of k minus x of k minus 1. So the L2 norm squared of x of k minus x is the L2 norm squared of x of k minus 1 minus x minus the L2 norm squared of x of k minus x of k minus 1. We have this inequality and that result. Take this L2 norm squared as a common factor. Between brackets, we have 1 minus the L2 norm squared of x of k minus x of k minus 1 divided by the L2 norm squared of x of k minus 1 minus x. We know that this is the magnitude squared of by minus ay transpose x of k minus 1 divided by the L2 norm squared of ay. We can write by as ay transpose x. So this is the magnitude squared of x of k minus 1 minus x transpose times ay. We have a square, so there is no problem in swapping the two terms. We can put this L2 norm squared here as the L2 norm of x of k minus 1 minus x. We also have this factor 1 over the L2 norm squared of ay. Condition on the indices of the rows employed from the beginning of the algorithm till x of k minus 1. For now, those are treated as constants. Take the conditional expectation with respect to y. Y is the index of the row that is used to obtain x of k from x of k minus 1. When we take the conditional expectation, this is a constant. We need to take the conditional expectation of this part. Now we make use of this inequality. Multiplying both sides by minus 1, we get that minus the expectation with respect to y of the magnitude squared of z transpose ay over the L2 norm squared of ay. This is less than or equal to minus the L2 norm squared of vector z divided by this product. In our case here, when we compute the conditional expectation, the fixed vector z is x of k minus 1 minus x divided by the L2 norm of the same vector. So the L2 norm of vector z is equal to 1. This bracket here is upper bounded by quantity that no longer depends on k. Specifically, the upper bound is 1 minus 1 over the Frobenius norm of a squared times the L2 norm squared of a dagger. Now we take the expectation with respect to the previously chosen rows. We get that the expectation of the L2 norm squared of the difference between x of k and x, the solution to the linear system of equations, is upper bounded by the expectation of the L2 norm squared of the difference between x of k minus 1 and x multiplied by this bracket, 1 minus 1 over this product. This bracket here is strictly less than 1. The Frobenius norm squared is the sum of the squares of the singular values of A. The L2 norm squared of A dagger is 1 over the square of the minimum singular value of matrix A. That's sigma n squared if the singular values of A are arranged in this order. By assumption, the rank of A is n, so sigma n is strictly positive, and this bracket is strictly less than 1. Note that sigma I squared is greater than or equal to sigma n squared. If we sum over the singular values, summation sigma I squared, I from 1 to n is greater than or equal to n sigma n squared. Divide both sides by n times the sum. So we get that 1 over n is greater than or equal to sigma n squared over the sum. Multiply by minus 1 and add 1. We get that 1 minus sigma n squared over the sum from sigma 1 squared to sigma n squared is greater than or equal to 1 minus 1 over n. Applying this recursive inequality repeatedly for k equal 1, 2, 3, and so on, we get that the expectation of the L to norm squared of x of k minus x is upper bounded by the expectation of the L to norm squared of x of 0 minus x. We don't need the expectation if x of 0 is deterministic. This expectation is multiplied by the kth power of this quantity here that is greater than or equal to n minus 1 over n, and that is strictly less than 1.